Hi, I'm Jonathan Crandall. You see me in such fine, quality, epic physics educational videos such as Work and Energy Chapter 8, Part 4, and Kinetic Energy and Potential Energy. What do they have in common with each other? Part 2. Okay, this is Physics Chapter 9, Work and Energy. I'm not going to finish off the entire chapter, but we're going to cover some main things here. So when we look at the idea of work, it's a constant force exerted on an object, times the object's displacement. Now when we talk about displacement, think distance. How much distance did the object move? So when we talk about an example of doing work, we're not talking about, oh, I did so much work on my project last night. That's not the kind of work. In physics, we're talking about you have an object that you are applying force, whether you're pulling the object or you're pushing the object a certain distance. So work is equal to force times distance. And the unit of work is the joule, J-O-U-L-E, and you're going to be seeing that a lot more. So here's an example. Sean is pushing a sleepy dog, mass of 25 kilograms, with a constant force of 300 newtons across the floor for a distance of 4.5 meters. Now there's some things we got to look at. We have a mass of 25 kilograms, we have a force of 300 newtons, and we have a distance of 4.5 meters. Now, and then they're asking us how much work did this dog, how much did this guy work, did this guy do pushing the sleepy dog? Okay, well, for one thing, work is equal to force times distance. So does the mass of the dog even come into play? No, it doesn't. Not for solving this problem. Now, you'd say, but wait a second though, the dog has a mass. You certainly have to push this 25 kilogram dog down the road. Well, right. The 300 Newton force is already taking that 25 kilogram mass into account. So that 300 Newton force is already pushing the dog. And because of that, we don't have to worry about the 25 kilograms. We don't have to worry about it. But we have a force, so we have 300 newtons. Here's our force. Okay, so there's our force. Okay, and we're trying to find work is equal to force times the distance. Well, our distance, they gave it to us at 4.5 meters, so 4.5 meters. Okay. And that's pretty much it. Now let's go calculate it very quickly. Okay, so 300 times 4.5 equals, and we have 1,350 joules of work has been done for pushing this dog that happens to weigh 25 kilograms 4.5 meters. Okay, so that's it for this first problem dealing with work. So, if we were to go and look at a second problem here, we have a group of fans are pushing the giant box of Grandmaster C's records across the hardwood floor. He pushes the giant box for 15 meters and does 4,500 joules of work. What's the force that's put on the box? Again, what's the important information that we have here? We got 15 meters, so we know that's a distance. They're asking us, what is the force? And 4,500 joules of work. Okay? So those are the pieces of information that I have. And I know that work is equal to force times distance. Now, there's a couple of ways to look at this. I could go ahead and plug in numbers right now and say, all right, I have 4,500 joules of work, and that's going to equal, well, I don't know what force is, but I'm going to put it up there anyways, multiplied by 15 meters. Or 4,500 is equal to 15 meters times force, or F. And then we can solve for F that way. So how do we solve for F with something like this? Well, if 4,500 joules of work is being done. We don't know the force, but we know it is 15 meters, right? That's what they gave us, 15 meters. There's a couple of ways I can do this. I could look force times distance is equal to work. So I could say work divided by distance will give us the force. Now, notice I went ahead and I did that with the formula before I plug in the numbers. Now, for some people, they would say, I don't go that way. All right, some people just go ahead and do this and say solve for F. And you can do that. But either way will work. So now I'm going to put my numbers here. I'm going to put in 4,500 joules of work divided by my distance of 15 meters. Okay, so with 4,500 divided by 15, and I go away with 300 newtons of force. That's it. That's what we have here, 300 newtons of force. And that's it for this one here, okay? So when we go on to the next one, we go on with the idea, ladies and gentlemen. Oops. Click. So we go on to the next one. Now, that was calculating work on a horizontal surface. Very straightforward, very easy to handle. Now, what if it is at an angle? Well, now, this is where we need a different formula. And the reason for that is looking at the formula here, work is equal to force times distance times cosine of theta. Well, let's look at it. If work is equal to force times the distance times the cosine of theta, how do we justify this? Well, if we're looking at, let's say we're pulling something. If we're pulling a wagon, let's say, all right, let's say we're pulling a wagon and we're pulling it with however many meters, okay? Here's the thing we got to look at, because when we're analyzing the work, this is the vector that we are interested in. We are interested in this vector right here. But wait, our main force is right here. Correct, because we're pulling this way, but we're interested in the vector going this way because that's how we can calculate the work being done. So that means, ladies and gentlemen, that there is some angle right here, the theta. Now, if we were to go and treat this exactly like a right triangle, where here's the force that we're pulling our little wagon, here's the vector we are interested in. The green vector is the one we're interested in because that's the horizontal part that is pulling this wagon across a distance. That's what we're looking at. Okay? So in this case here, when we look at Sohcahtoa, all right, our force here, that's got to be our hypotenuse, guys. That is our hypotenuse, which means this angle here in question, this has to be our adjacent, and this is our opposite. So when we look at this, it is, so if we were to go and look at this triangle here, okay, let's remove it here. Let's move that triangle here where we have our green, we have our black, and we have our blue, just like this, and we have our theta there. Okay, this is where the Sohcahtoa comes in, because this is our force that we're pulling with. That, guys, is the hypotenuse of our right triangle. Here's our angle we're interested in. Guess what? This is our adjacent to the right triangle, and this is our opposite. So when we are looking, ladies and gentlemen, about the sine, the cosine, and the tangent, we're looking here at the green because that's the one we need to find to pull the wagon That's the ka. Cosine, adjacent divided by the hypotenuse. So that's why we've got to use the cosine of whatever thing that we've got there. Now, let's go back and look at the problem. So Josh is pulling Alex's car, which broke down. He pulls it with 500 newtons of force at a 25-degree angle. Okay, so I have a 500 Newton force. I have a 25-degree angle, so they gave me a theta, and then they gave me a distance of 200 meters. How much work did he do? Okay, so with it, 500 newtons, 25, and 200. So let's move on here. We have a 500 Newton force. Okay, that's our force. Our theta is equal to 25 degrees. And our distance, I've got to go back and check, our distance is 200 meters. Okay, so 200 meters equals the distance. Okay? All right. So now we've got that, and we've got all the pieces. Now we just got to figure out how to work this. So work is equal to, what's our force? Well, we have 500 newtons. Okay, we're going to multiply that times our distance of 200 meters. Now, do you have to put the units in there? No, you don't, unless that helps you to keep track of what's going on, times the cosine of 25 degrees. Now again, remember, what is the 25 degrees that cosine going to do? It's going to make our force of 500 newtons a little bit smaller. Well, why? Well, remember, going back up here, when you're pulling the wagon, you're pulling it with this force, but we're interested in this force vector. And that's why we got to work with the cosine. This is going to be our full force of 500 newtons. This has got to be less than 500 newtons, folks, because it's going horizontally, whereas the main force is going at the angle. That's what's going on. So, with that, guys, let's go ahead and let's check that out. So 500 times 200, okay, and that gives us 100,000, okay, newtons times meters, and then we're going to multiply by the cosine of 25 times the cosine of 25, okay, and that's going to give us 90,630.8. Okay, that's how much work. That's joules. 90,630.8 or 90,631. Whereas the cosine of 25, ladies and gentlemen, for those people who are wondering, is 0.9063. So, keep in mind, guys, remember when your calculator, you want to make sure that your calculator is in degrees, not radians. Okay, I'm running a little short on time here, so I got to make sure I have gotten this out. Okay, so that should take care of work. Okay? Okay, when we look at the next one here, all right, Jimmy is pushing a box of broken beakers, thanks to AP Chem, at an angle of 30 degrees over a distance of 100 meters and doing 1,200 joules of work. How much force did he use to pull the box of broken beakers? Okay, so we gotta look for force. So I know that work, is equal to force times the distance times the cosine of 30 degrees. So I have my 30 degrees here, excuse me, I have a distance of 100 meters and 1,200 joules of work. So I could just go ahead and say, all right, I have 1,200 joules of work is equal to force, which is what we're trying to find, okay, times the distance, which is 100 meters, times the cosine of 30 degrees. Okay? So cosine of 30 is 0.8660. All right. Times 100 equals, okay. So that gives us 1200 is equal to 86.60 times F. So we can say 1200 divided by 86.60 equals. Okay? So 1200 divided by 86.60, and we walk away with 13.86. Wow, that's not a lot of force that's put in. Okay, yeah, not a lot of force that's put in, but it's moving the box and it's getting the job done. Okay, well, that's it for the first part of Physics Chapter 9. Okay, as I am running out of time here, so we covered work for Chapter 9. All right, take care.